For more physics-related videos, please subscribe. Welcome to Stellar Physics 3A. In this video, I will go over hydrostatic equilibrium. First, I will derive the equations for hydrostatic equilibrium. Then I will solve them in the case of constant density. And then we'll take a look at how to solve them if the density is not constant. I rated the physics level in this video as intermediate. Before we begin, we're going to make a few assumptions. First, we're going to assume that the star is static, meaning it's neither contracting or expanding. We're also going to assume it's spherically symmetric. We're going to assume that Newtonian gravity is sufficient, meaning that corrections due to general relativity are negligible. Mathematically, this means that everywhere inside the star, the quantity 2gm over rc squared is much less than 1, where r is some radial position, m is the mass enclosed inside that radius, g is Newton's constant, and c is the speed of light. This quantity is often called the metric deviation, so in case I refer to it that way, you'll know what I'm talking about. Eventually, we will also assume what's called a polytrope solution, and we will also assume that the ratio of the gas pressure and radiation pressure is constant throughout the star. This is sometimes called the standard model of stellar physics. So, hydrostatic equilibrium. So if we draw a star at some radial position inside the star, this will define a sphere that encloses some mass, which I'm going to call m of r. So m, which is a function of r, is the mass enclosed by this sphere of radius r. Now let's say the sphere has a very thin thickness, which I'm going to call dr. So essentially what we have here is a shell of radius r and infinitesimal thickness dr. And the mass of this shell I'm going to call dm. The gravitational force on this shell will be the mass of the shell times the gravitational acceleration, and g of r will be entirely determined by the mass enclosed inside this shell. Due to spherical symmetry, the mass outside of the shell will exert no net gravitational force on the shell. The material inside the shell will exert an outward pressure on it, and the material outside of the shell will exert an inward pressure on it. And since the outside pressure is being exerted at a slightly different radius than the inside pressure, these two pressures will be slightly different. Now we've assumed that the star is static, hence the term hydrostatic equilibrium, so that means that the sum of all the forces on the shell must equal 0. So the sum of all the forces will be the inside pressure times the surface area of the shell, minus the outside pressure times the surface area, and minus the gravitational force. These minus signs account for the fact that these two forces point inwards, while this one points outwards. And the sum of all the forces has to be 0. By Newton's law, the gravitational acceleration will be Newton's constant times the enclosed mass divided by the radius squared. And the outside pressure at position r plus dr, we can write as the inside pressure plus a small change in pressure. When we plug this into our equation for the sum of the forces, we get that a small change in pressure times the surface area of the shell, which is 4 pi r squared, must equal the gravitational force on the shell. In general, the mass enclosed will be the density integrated over the volume. We're assuming spherical symmetry, and so we're just left with the radial integral. We can differentiate both sides to find an equation for dm of r. This equation is generally referred to as the mass continuity equation. We can substitute this into our equation for the pressure. The surface area terms will cancel out, and dividing on both sides by dr, we get the following differential equation for the pressure. So we can now summarize a general system of equations for hydrostatic equilibrium. I'm first going to write them down in the most general case, meaning in absence of spherical symmetry. The equation we just derived for the pressure can be written more generally as the gradient of the pressure equals the gravitational acceleration times the density. The mass continuity equation in general can be written as dm dv equals the density. This is actually just the definition of density. And finally, as we found in previous videos, we know that the pressure is some function of density and entropy. If we assume spherical symmetry, the gradient will reduce to a radial derivative, and the mass and density will only be functions of radial position. And although this doesn't actually have anything to do with spherical symmetry, we're going to assume that the pressure is related to the density via what's called a polytrope. We'll see in a little bit what that is. Now, as far as hydrostatic equilibrium, that's all the information you need. But if you want a more detailed understanding of the internal structure, you need a little more information. You need to conserve energy, and this means that the nuclear energy produced must equal the energy released by the star, which is going to be the photon luminosity plus the neutrino luminosity. This equation holds only in the case that the star is static. If the star is not static, you have to include other terms to account for kinetic energy, changes in gravitational potential energy, and changes in internal energy. You also need to know how heat is transferred throughout the star, which could be either by radiation, convection, or conduction. If you're enjoying this video so far, please be sure to like and subscribe, and maybe share it with a few friends. Now that we have a set of equations for hydrostatic equilibrium, let's start off simple and start in the case of constant density. In this case, our differential equation for pressure will look the same, it's just that the density will be constant, and the mass enclosed will just be the density times the volume. So let's plug m of r into the pressure equation. 2 powers of r will cancel, and now we can easily integrate this. P naught here will be the central pressure, so when r equals 0. In order to find this value, we need a boundary condition. I'm going to pose the boundary condition that the pressure at the stellar surface is 0. This doesn't have to be true. You could imagine maybe the pressure is not 0 at the surface, either because maybe the star has an atmosphere around it, exerting some atmospheric pressure, or you can maybe imagine having some surface tension. But assuming that the pressure is 0 at the surface of the star, this gives us the following equation for the pressure, which can be rewritten in terms of the mass of the star by substituting that the density is the mass divided by the volume. How the pressure will relate to the temperature will depend on if the star is radiation dominated or gas dominated. I'm not going to do that because in reality, constant density is a pretty bad model for a star. This equation, however, wouldn't be too bad for something like a rocky planet, where the constant density approximation is not that bad. It's also not a bad approximation for compact objects, so you could get away with this for dense cores and white dwarfs. Constant density also works pretty well for neutron stars, but in the case of neutron stars, the Newtonian approximation doesn't hold. Neutron stars have a metric deviation that's very close to 1 and are basically on the brink of collapsing into black holes. So now that we have a solution for constant density, let's take a look at a more realistic case, which is that the density is a function of r. So let's start off with our two equations, the equation for pressure and the mass continuity equation. I'm going to rewrite this first equation by moving the r squared here to the other side of the equation. Now I'm going to differentiate both sides. On the left-hand side, I'm going to leave it as the derivative of r squared times dp dr. On the right-hand side, I have to use the product rule to differentiate both m and rho. So this term here will be the derivative of m while holding rho constant. And this term here is the derivative of rho while holding m constant. Now I'm going to substitute the two original equations into these two terms. So in m of r, I'm going to substitute this first equation, because you can see I have an m of r here, so I can isolate it by bringing everything to the other side. And here I have dm dr, so that's just the second equation. This will give us the following equation. Now I'm going to divide both sides by the density, and I'm going to bring this second term to the other side of the equation. If you take a close look at the left-hand side of this equation, you'll notice that it's actually a total derivative. So looking inside these brackets, we see we have two terms. We have this 1 over rho, and then we have this term inside the parentheses. The first term over here is holding 1 over rho constant, times the derivative of the term in the parentheses, and this second term is holding the quantity in the parentheses constant times the derivative of 1 over rho. That includes this minus sign here. And so we've combined these two equations to one second-order differential equation for hydrostatic equilibrium. So now, in order to go any further, we need some kind of way to relate the pressure to the density. And this is where we're going to assume that the pressure and density are related via what's called a polytrope. And that means that the pressure is equal to a constant K times the density raised to another constant. Solving this equation using a polytrope is not particularly difficult, but it's a little time consuming and there's a lot of different parts that you have to keep track of, so I'm going to do this in a separate video. If you enjoyed this video, like and subscribe, and be sure to hit the bell to be notified for future videos in the series.